Hello, this video is going to be about system identification, but more specifically, it's going to be about the algorithms that I use for system identification and the advantages and disadvantages of the different algorithms. There are 7 that I'm going to look at today. But what we want to do is see what we're trying, well, this is what we're trying to do is identify a nonlinear valve. And I chose a nonlinear valve because it's difficult. It's not easy. If you look at the internet, you'll see a lot of examples where they have an equation for the system they want to identify. And it's very easy to take the derivative of that and get perfect solutions in very little time. This is working with real data. It's not linear, and it's prone to noise and other flaws. Big thing is that it's not linear. So what I have done is we've got a swept sine wave, which is the control output, this green line, and then we have the perfect or the actual positions, which is the solid blue line underneath. And what we're trying to do is come up with a model that generates this red line that acts exactly as the blue line, the actual system, as a function of this green line. And the reason why we want to do this is so that we can uh, get a model of the system. I can see how linear it is. So I know that if I want to go 6 inches per second, this is how much I have to apply in the uh, positive direction, and well, this is how far I will go in the positive direction with about 60 or 75% output. So this tells me how I need to compensate for the nonlinearity of the valve when I'm trying to control a system. So let's look at the different models now. Let's see, this one is Levenberg Marquard. Okay, the Levenberg Marquard system is one of my favorites, and it's the one that we use in our product. It's very, very fast, and it converges very, very quickly. So I will just run this for a second, and while I'm running it, I'm going to explain the different parts of the model. So I got plotting the model and the valve and the valve response, and you've already seen the graphs for that. I have to initialize parameters. I've got a routine to print the parameters, but basically what I'm doing is I've got this differential equation here, and it's got 10 different segments. I've got 4 in here, 2 here, 2 here, 1 here, and 1 here. And what this allows me to do is it's a piecewise linear model. I've tried other models, and this one ended up working the best. So let's go back to where I was. And, and you can see that I got what it does is it starts out with a guess as what these 15 parameters happen to be. The 15 parameters happen to be a ratio. This is A1 is the damping factor times natural frequency. This is the natural frequency squared, the dead time, an offset, and then there's the 10 gain segments. And what it does is it makes an initial guess and it computes the mean squared error between the model and the actual data. And the mean squared error came out to be 0.037. And what it does is it has to take a step for each one of the parameters in each direction and figure out the gradient and then move along that slope to find a better solution. So to give you an idea what this is like in 2 dimensions is that assume you have only 2 parameters that need to be optimized. One you can kind of think of as being a north-south parameter and the other being an east-west parameter. And the sum of error squared or the mean squared error is the elevation above zero, sea level. And what you want to do is you want to find the x and y coordinates, north-south, that will get you to the lowest position or the lowest elevation. So if you can see, it would make it easy because you know what direction to go, but the computer cannot see. So what it does is it takes a step to the north, and step to the south, step to the east, step to the west, and then it kind of figures out what direction it can go, and then it starts going in that direction until it can't go any further. So you can see that initially the Levenberg Marquard algorithm did the 15 steps, and then it made a huge increase, or actually decrease, in the cost function. And you can see that then it's making another huge decrease. That's almost a factor of 4. And if we run this for about 6 minutes, um, we will be able to see it converges. So this is my differential equation here. I use a ODE int. This is the differential equation, my initial assumption for the uh, parameters. And then I have the time, and also this is the parameter array. And then it gets optimized by the ODE int. What it does is it figures out a mean squared error, and that gets returned to the min error routine, which then optimizes that, or it tries to minimize the mean squared error. It just adjusts the parameters so the mean squared error is minimum. And this will come up with an answer fairly quickly. Now, I really like the Levenberg Marquard. Like I said, it's what I use in my systems, but what it doesn't like is it doesn't like bounds. And also, it works a little bit different from the other algorithms that I'm presenting today, because what it does is it works on the difference between the actual position and the estimated position. So this is the actual position. That was the cyan line. This actual position is the dotted red line, and I get a difference. I'm computing the mean squared error and displaying it here only for informational information. And then what happens is that it returns this diff to the minimizer program. And like I said, Levenberg Marquard is the only one that works off of differences. The other algorithms work off a cost function, and the cost function can be any kind of cost function where you have multiple things that you might want to compare and have different weights. Kind of like if you're doing a LQR or something like that, where you're trying to minimize that function. So the Levenberg Marquard is very efficient. It doesn't like bounds, and it works off the differences. So now I'm going to look at a different algorithm, and this is going to be uh, the Nelder-Mead, I believe. Yep, Nelder-Mead. Okay, well, I actually have 5 algorithms in here, and I'm going to explain the advantages and disadvantages of each one. The Nelder-Mead will work off of bounds, and of all of these other ones, only the uh, congruent gradient will use bounds, and also the gradient descent, which I haven't shown yet, that will work off bounds. So what will happen is that you can see that right here, the gains should be 0, and I have the limit for the gains set at 0, and the Levenberg Marquard will not like having the gains set at 0. So a trick that I use is to use more than one optimization routine. So let's go back. Let's see, that's the Levenberg Marquard. This is the, okay, here we have the Nelder-Mead. What I like about the Nelder-Mead is that it will work with the bounds, so you can use the Nelder-Mead to kind of finish up. Now the Nelder-Mead is another algorithm that I like a lot because it doesn't depend upon derivatives. Of course, neither does the Powel or the congruent gradient. But the Nelder-Mead is kind of a brute force and stupid way of optimizing. Uh, in this example, I've got 15 parameters. So what it does is it generates 16 points, and it figures out the mean squared error for those 16 points. And then what it does is it takes a look at the worst one and it moves it towards the center of the other 15. And if it likes the solution that it has so far, it will try to move it some more. But eventually what happens with the 15 points is that they all end up collapsing along or among each other. And so therefore the steps that it takes end up being very small, so it takes a long time to converge. But the best part is that it doesn't rely on derivatives. So it's a good algorithm to get started, because if you end up with the, like say the Powel algorithm, or maybe the L-BFGS, sometimes it goes off in directions which can cause the sum of errors squared or the mean squared error to blow up, become too big, and you get a fault. And the Nelder-Mead can at least get you into the ballpark pretty quickly. The Levenberg Marquard is really good at getting very, very close, but then it doesn't take into account the bounds. You can then restart the Nelder-Mead, and it will take into account the bounds, and it'll get you right into the position. Another algorithm I like is the BFGS. This is the initials of the 4 people that invented it, and it uses derivatives and inverse Hessians. It's very, very fast. It converges quickly, kind of like the Levenberg Marquard. It doesn't like bounds. And again, the Nelder-Mead is a good algorithm for getting it back into the, well, it'll take into account the bounds. So it'll correct for any time that the BFGS algorithm has gone over the bounds. The L-BFGS-B algorithm is similar to the BFGS, except for it's meant for sparse matrices, and it's more memory efficient than what the BFGS is. However, this algorithm tends to blow up more easily, and again, it would benefit by being using the Nelder-Mead to get into a local area before, so that it doesn't blow up, and then also finish with the Nelder-Mead. But a lot of the optimization can be done with the BFGS. Now, some of these algorithms will take like 6-8 minutes, and others will take hours. The Powel algorithm and the congruent gradient algorithm are the same, or almost the same, except they both rely on choosing an arbitrary vector and then doing a line search till you find a minimum, and then using that information and the previous search to find a new direction to get to the middle. It doesn't use derivatives. What I don't like about the Powel method is that when you have 15 parameters, it doesn't work very well. It works real well with the examples you see on the internet, where there's maybe 2, 5 parameters, but it doesn't work very well with 15, because defining a line that goes through 15-dimensional space is kind of, well, it's not easy, and it doesn't work well. And same thing goes with congruent gradient, but it works a little bit better than the Powel, plus it works with bounds. The final one I'm going to look at is the gradient descent. And the gradient descent basically finds the derivative for each one of the 15 parameters and starts taking a step in that direction. So here I've got it calculates out the mean squared error, and then, oops, that was the solution that we had before, and you can see that it turned out well, and it was about 6 or 8 minutes. And there's my linearity. And so what happens here is that we figure out a gradient, or basically the derivative of each parameter, and then we have this learning rate, which you multiply by the gradient to modify the parameters. Then I do a bounds check, and then I calculate the mean squared error after I do the bounds check, and then I do a line search. Now, I do a line search. A lot of the examples that you see on the internet use what they call the momentum, which basically uses the last different gradient to add some factor of it to add to the new gradient. So what happens is that you have a little bit of momentum from the last gradient determination. But I've tried that and it doesn't really work all that well. What I like about the line search is once you find a direction, you can keep on going in that direction until you no longer see the mean squared error. Well, as long as the new mean squared error is less than the old one, you just keep going, and you can see I got bounce checks here. So the gradient descent works with the bounce check, and again, this will take about 10 minutes or so. So uh, these algorithms are not very fast. They all have their advantages and disadvantages. Oh, one more thing is that the gradient descent is often used by um, neural nets for training neural nets and finding the weights. So again, we have seven optimization routines. There is the Levenberg Marquard, one of my favorites. There's the Nelder-Mead. That's one of my favorites because it doesn't require derivatives and it can handle the bounds checking. It just converges very, very slowly. Um, and then there's the Powel and the congruent gradient. Powel will probably work very well for only optimizing 4 or 5 parameters. Same with this one. But I don't really like these. They're not my first choice. Again, in this list, I like the Nelder-Mead and the BFGS. And then finally, there's a congruent gradient, which is used for training neural nets. It's not really my favorite because it's kind of silly, or it's not very intelligent in the way that it does things. So again, my favorites are Levenberg Marquard, the Nelder-Mead, and the BFGS. And one more thing, the Levenberg Marquard is its own package in Python. It's called LMFit. The gradient descent I wrote myself. Uh, I couldn't find a package for it, a Python package, so I wrote it myself. And then BFGS is part of uh, the minimizer function that comes with SciPy. So if you have any questions, ask them. This concludes my video.